All right, bonding and electronegativity. So, by definition, electronegativity, right, is the ability of an element to gain or to attract an electron. So we've talked about it on the periodic table, and you have this little chart for electronegativity values, right? We've said that the elements that are more to the right have more valence electrons. So for example, the alkali metals right here, right, they only have one valence electron. So they're looking to take that one electron and give it away. So they're not really looking to attract anything. Whereas the sevens here, okay, they are desperately looking to gain one electron. They want to attract one because they have 7 now, the halogens do, and they would want to gain one to get to 8. Now the reason there's no noble gases on this electronegativity values chart is because, let me remind you, they already have 8, right? So they've got their octet full, and they don't want to attract any electrons either. So they have no electronegativity at all. Okay? So it makes sense that, something like fluorine here with an electronegativity of 4.0 would be greater than something like lithium with 1.0, or even furthermore, something like cesium. Because remember, our trend here goes increasing bottom to top and increasing left to right. So our largest is here in the upper right-hand corner, the nonmetals, and our smallest is in the bottom left with the alkali metal here of cesium. Alright, so bonding and electronegativity. So I am going to spend a few minutes talking about page 12. And so, first of all, what I need you to know is this. Ionic. If you see with ionic substances that you have a metal and a nonmetal, then your substance is ionic. Again, it must have a metal bonded to a nonmetal. How am I going to know that? Remember, to the left of our staircase are our metals, to the right are our nonmetals. There's a lot more metals than there are non. And in general, the electronegativity difference between them, okay, will be 1.5 and above. So 1.5 plus. Which brings us to two types of covalent bonds. Remember, with covalent bonds, the bonds are going to be created by the sharing of electrons, right? And so this is between nonmetals. And there are two types of them. There are polar covalent and there are nonpolar. So when you share something, sometimes we don't exactly share it in an equal way. And so when I think of polar, here's what I think of, right? If I think of two people that are polar opposites, means they're not the same, right? They're still people, but they have different qualities. So when I think about polar, I think of my sister and I when we were little, when we were 16. I was 17 at the time. And we shared a car, right? 1989 Buick Century. And even though we shared the keys to that car and we shared that car, I was a year older, I was involved in a few more sports, so we were sharing it, but it was not equal. So it was a polar relationship, right? She always kind of resented the fact that I got the keys more than her. And in retrospect, maybe that wasn't fair. But this is an unequal sharing. Now, in order to claim something is polar covalent or nonpolar covalent, and I guess this would be an equal sharing, so let's be thorough. Two things must occur. First of all, polar, you have to have nonmetals. Nonpolar, you have to have two nonmetals. If both things do not apply, then you can't do it. And we have a couple of ranges, okay? For polar, our range is going to be this. For a polar covalent bond, it's going to generally be between 0.41 and 1.49. Right? So pretty much up to 1.5. For nonpolar, that's going to be from 0.0 all the way out to 0.40. Okay? So our range again will be to 0.4 nonpolar, 0.41 to 1.49, and 1.5. But both things have to apply. Meaning to be ionic, you have to have a metal and a nonmetal and 1.5. Okay? What I would also say is this. Sometimes you'll see some weird exceptions with polar, and you might even see a couple with ionic. But these are general assumptions. So you have an example on your sheets, okay, and let's do one together. And it's Li and Cl. Well, lithium is a metal. Lithium is found on the left side of the periodic table. It's right here. Okay, it's an alkali metal. It has one valence electron, therefore it's looking to get rid of it. It has a low electronegativity of 1.0. Chlorine, on the other hand, is way over here. Chlorine to halogen. Okay? And chlorine has an electronegativity value, according to this chart on page 13, of 3.0. So this is pretty simple. What we do is we look at the bonds and we say to ourselves, okay, what would be the difference between the two? So we take 3.0 minus 1.0, and that's 2.0. Now, this is a metal, this is a nonmetal. So metal and nonmetal, it's greater than 1.5, so the type of bonding is ionic. Let's look at another example. Fe2O3. Now this is kind of tricky, right? You have 2 irons bonded to 3 oxygens, right? So what you have to do is you're going to have lots of bonds here, but they're always going to be between the irons and the oxygens. So what I don't want you to get caught up in is the 2s and the 3s. You want to get caught up in this, the iron versus the oxygen, because those are the 2 elements that are bonding. So when I go on my electronegativity chart, I find iron and it's 1.8. Then I go find oxygen on here, and oxygen is 3.5. Now, when I look on here, if I find my staircase, I can analyze that iron is 1.8, it's in the transition metals. Oxygen here is to the right of the staircase, and as such is a nonmetal. The difference between 3.5 and 1.8 is 1.7, so that also makes sense. So we have a metal and a nonmetal. Metal, nonmetal, greater than 1.5, and it is ionic. Let's do another example. Ugh, doesn't look so good. Alright. The next example, let's jump down to where it says NO2. Okay? So when we find nitrogen here, nitrogen, oh, we're to the right, so that's 3.0. 3.0. And oxygen is also to the right, and it's 3.5. So now we have 2 nonmetals. It is now covalent. We got to figure out now, is it polar or nonpolar? Are they an unequal sharing of electrons or a perfectly equal sharing? Well, when we look at the differential between 3.5 and 3.0, it's 0.5. That falls in this range right here, doesn't it? Therefore, by definition, NO2 is polar covalent. Let's do one more. O2. Now, this is tricky. This is the first time where the number actually matters, because here, the oxygen, it has to be bonded. It's diatomic to itself. It's the only thing it's possible for. So this is one oxygen bonded to another oxygen. So what ends up happening here is this. You end up with a 3.5 oxygen bonded to another one. So it's 3.5 minus itself 3.5. And the differential there is 0. Oxygen is a nonmetal, oxygen is a nonmetal, therefore we're still covalent. And then when we go look at our chart tells us 0 to 0.4, this is non-polar covalent. Hopefully that's enough examples for you to complete this page.